Christina. I'll be talking about doping MoS2, measuring work function, shift due to this doping, the limits of KPFM for these measurements, and what we're doing instead that's better. We want to tune the work function of MoS2 and other two-dimensional materials through doping because this gives us flexibility in the design of stacked 2D material devices in the future. However, doping after growth often will degrade carrier mobility, so we want to dope during growth. The MoS2 flakes that were used in this work were grown by CBD in our collaborator Jing Kong's lab, using different precursor ratios and different gas environments to get different types of MoS2. For example, using extra sulfur during the growth, we get sulfur-rich MoS2. Flowing oxygen during the growth results in oxygen-rich MoS2, and we can also grow undoped MoS2. After growth, we put these into a backgated FET geometry. We do this so that we can extract bulk electrical properties of our materials through gate sweeps. We can see from our gate sweeps, looking at the threshold voltages of sulfur-rich MoS2, this has the lowest threshold voltage. For oxygen-rich MoS2, this has the highest threshold voltage, and undoped MoS2 sits in between. From these gate sweeps, we can also extract carrier mobility and see that doping has not degraded our carrier mobility. And the shift in threshold voltage suggests a work function shift, but is not a direct measure of this. So we would like to measure this directly. This is typically done through Kelvin probe force microscopy, KPFM, where the force between the tip and the sample is zeroed by applying a DC voltage to the tip. To do this well, we want to have a reference material in our scan. So we always keep part of a grounded gold electrode in our scan when we're measuring the work function of MoS2. For our air-sensitive MoS2, we also want to take these measurements in nitrogen. On a good day, we get KPFM potential measurements as seen on the right, where the potential is flat on any given material, and both of our grounded gold electrodes are at the same potential. We can see from this potential results actually some useful information. We can see that the MoS2 is at a higher potential than the gold, and thus a higher work function than the gold. And we can see the difference in work function of multi-layer MoS2, seen on the bottom right, bottom left of the potential scan, and the top center of our potential scan, compared to the potential of monolayer MoS2, which is the bright regions of potential. However, a lot of the time, our KPFM potential measurements will have a tilt and a curvature to them. We can see here that this results in the grounded gold electrodes looking as though they are at a different potential, even though they are the same material and at the same voltage. This is concerning. We suspect that this is due to coupling not just between the tip of the AFM and the sample, but also the cantilever and the sample. Because unlike materials of interest where they would extend 4 millimeters, even though the tip of our sample is over gold and MoS2, most of our cantilever is over insulator, which has a much less well-controlled potential and much less certain potential, as opposed to our grounded gold electrodes. So the question is, how do we still measure work function while minimizing this problematic coupling of the cantilever to our sample? For KPFM, we are taking our topography scan, lifting up the tip, and measuring the force between the tip and the sample. But for EFM, electrostatic force microscopy, once we lift up the tip, we are instead measuring the frequency shift of the oscillation of the tip while applying a DC voltage to the tip. And when we substitute in for the capacitance of a parallel plate capacitor, which we can model our cantilever and sample as, we can see that we have less problematic coupling of the cantilever to the sample with EFM because we have z to the -3 dependence versus z to the -2 dependence of KPFM, where z is our sample tip or sample cantilever distance. We, instead of measuring a frequency shift, are going to measure a shift in phase, but our z dependence still remains, and our ability to measure work function, just like with KPFM, still exists for EFM. So what this looks like is measuring the phase while applying different tip voltages, as can be seen on the right for -5 and 3 volt tip voltages. We can see that the phase is different on each of our materials for these different tip voltages. In order to extract the phase on each of our materials, we mask off so that we can only see one material, taking care to avoid the interface and the start of each of the scans. We can fit the resulting pixels to a Gaussian by taking a histogram, or by taking the average pixel value and taking the standard deviation of this. We get comparable results for each of these methods. We can plot these phase values for each material as a function of tip voltage and see that they have a parabolic shape due to the v-squared dependence on the phase shift. We can fit these to a parabola for each material and take the derivative in order to extract the tip voltage associated with the minimum phase and thus minimum phase shift for each of our materials. And we can see that, like for KPFM, a higher measured potential corresponds to a higher work function. So in this case, our MoS2 is at a higher work function than that of gold. We can look at the difference in potentials associated with the minima for our gold and our MoS2 and use this potential difference as a proxy for work function difference between gold and MoS2 and compare this between different flakes using our gold as a reference. We can do this for undoped and oxygen-rich MoS2 and see that the difference in minima between gold and undoped MoS2 is rather small, whereas the difference in minima between gold and oxygen-rich MoS2 is considerably larger. This indicates that our MoS2 is at a different work function when it is oxygen-doped versus when it is undoped. We can do this a bunch of different times, and we can extract average potential differences, again corresponding to work function differences, and see that for undoped MoS2, our potential difference is about -10 millivolts, whereas for oxygen-rich MoS2, our potential difference compared to that of gold is 250 millivolts, suggesting that we have successfully shifted the work function of MoS2 by oxygen doping during growth. And this is actually completely consistent with what we see from bulk IV measurements and from DFT. So what we have shown is that we can tune the work function of MoS2 by doping it with oxygen during the growth without degrading the carrier mobility. We have demonstrated that EFM is a superior technique to KPFM for these flakes due to the z⁻² dependence of KPFM versus the z⁻³ dependence of EFM, which is minimizing the coupling between the cantilever and the sample. And we have shown that we can get a 260 millivolt shift in the MoS2 work function due to oxygen doping, as measured by EFM. What we would like to do in the future is measure the work function of sulfur-rich MoS2 with EFM. We would like to measure the variation in work function over individual flakes. As we can see on the right, basically measuring the potential at different locations on, in this case, an undoped MoS2 flake. And what we are the most excited to do is to use EFM to measure the density of states of our differently doped MoS2 flakes and compare the defect states in our sulfur-rich and our oxygen-rich MoS2 compared to our undoped MoS2. The way that this works is we apply a backgate voltage to our sample and measure the potential on the MoS2 as a function of how much basically backgate voltage we apply. When we apply a backgate voltage, we are functionally pouring more electrons into our material so that it is now occupied up to a higher energy level. Based on how much this energy level, as in how much this potential shifts as a function of a certain amount of electrons poured into it, we can get a sense of how many states are at a given energy level. So we are very excited about this possibility. I would like to thank the Ayadala Lab at Mount Holyoke, the Kong Lab at MIT, and all of the funding and the user facilities that have made this work possible. Thank you so much.